So 9, 5 is your polar coordinates. Shh. So we learned how to plot something on a polar coordinate grid. The polar coordinate grid, which looks like this. Shh. All right, so it's almost like a unit circle with a bunch of rings on it, okay? Each ring represents a radius of 1, and then obviously your unit circle angles are there. So the way these are written is r theta. R stands for a radius, and then theta is your angle. So if I said 3 pi over 4, then I go to 3 pi over 4 on my unit circle, which is on the left, and I would go to the third ring, 1, 2, 3, and I would literally plot a point. That would be that point. Kevin.
Where do I get that picture
from? If you go to the 9-5 homework assignment, I put it on the assignment.
9.5.
9-5 homework. I put it on the assignment. Yep.
Okay.
If the radius is negative, what happens? It goes to the opposite ray. So same angle. If I did 3 pi over 4, I would still normally go to 3 pi over 4, but if it's a negative 3, instead of going towards it, I go the other direction, and that one would be there. Okay, so the first thing we learned was how to plot them. Then we learned how to find additional polar representations of them. So if it says find 3 additional polar representations of this same point, meaning give me other ways to name the same point. And because these coordinate points are coterminal, we literally just keep going around our circle. So there's 2 ways to do it. One is keep R, meaning if it was a positive 3, it stays a positive 3. If it was a negative 3, it stays a negative 3. And then take your theta and add and subtract even multiples of pi. We start with 2 pi, but let's say you wanted to find another one, you could add 4 pi. You could subtract 4 pi. That would still give you another polar representation of the same point. The other option is to change the r. So I change it from positive to negative. And I take theta and I add or subtract odd multiples of pi. Meaning I can add pi, or I can add 3 pi, or I can add 5 pi. And then we did 2 conversions, from polar to rectangular and rectangular to polar. So from polar to rectangular, I'm going r theta to xy. It would be r cosine theta, r sine theta. So whatever your radius is, you're going to multiply it times the cosine of that angle, and then you're going to take your radius again and multiply it times the sine of that angle. Yeah. Yeah, well, you'll get given it to graph this question, so it will be on there. And then you'll get given it to graph the other polar functions. Yeah. Correct, which has the angles on it. Yeah. All right, then we went from rectangular to polar. And this kind of broke into 2 parts. To find the r, we do the square root of x squared plus y squared. And to find theta, the tan of theta equals y over x. So we do tan negative 1 of y over x. It would actually give you 2 answers. If I said theta was, or I said the tan negative 1 of root 3, there's 2 answers for that. So then we determine which theta it is. There's only one right answer based on the location of the original coordinate point. So if my original coordinate point is in the first quadrant, then I pick the angle that would be in the first quadrant. If my original coordinate point is in the third quadrant, then I pick the angle from the third quadrant. And we said obviously we need to know our unit circle angles. Our over 6 is are root 3 over 2 and 1/2. And our tangent is root 3 over 3. Our over 4 is 1/2 root 3 over 2. No, my goodness, sorry. Our over 4 is root 2 over 2 and root 2 over 2. And our tangent is 1. And our over 3 is 1/2 and root 3 over 2. And our tangent is root 3. So this is my cosine, this is my sine, and this is my tangent. And all students take calculus, tells you the positive or negative sign on those values. All right, now came 9-6. Okay, so this we did over the course of 2 days. It was a lot of content. I'm going to try to review it, but listen. There are 4 types of polar graphs that we covered. The first thing that we talked about was the test for symmetry, okay? And this applied to all of them except for the lemniscate, because the lemniscate has an r squared, but we'll talk about that in a little bit. Okay. If your function is an r equals, so for all of these, if it's an r equals, an r equals, an r, well, I'll make that the r squared, okay? If it's an r equals and it has cosine in it, all right, so if it's a cosine, then it has symmetry to the polar axis, which means I can fold it along the x-axis, because we now call that the polar axis, and it would be symmetric, so top to bottom. So if your graph has symmetry to the polar axis and you need to plug in points, I would plug in points from the first and second quadrant, and then I would literally reflect them down underneath. So knowing your symmetry is going to eliminate half the work for you, and also on your test, it's going to ask you to classify your polar function, give it its name, and then tell the symmetry. If it has sine in it, then it's symmetric to the pi over 2 line, which was what was called your y-axis. So if I had something that was symmetric to the pi over 2, I would plug in something from the right side of my graph, and then I would flip it over the y-axis or the pi over 2 line. The pole is the origin, the point in the middle. Yep. Which brings to the last one. If it's an r squared, okay, which is a lemniscate, or it's an r with, that's a rose with an even amount of petals. Actually, the r squared, it's symmetric to your pole, which means anything that happens in the top right gets reflected down in the bottom left. And the same color. And anything in the top left gets reflected into your bottom right. And then, I shouldn't say or because these are different. And then the r equals a rose with even amount of petals, which we're going to talk about in a second. It's symmetric to all 3. Okay, which means polar axis, pi over 2, and pole. R is the pole. So like this is your infinity symbol. If it's in the top right, it finishes in the bottom left. If it's in the top left, it finishes in the bottom right. It could be on your x-axis or your y-axis though, too. All right, now let's go polar graph by polar graph. Okay, the ones we started with were the circles. Okay. And these only had the trig function. Something could be multiplied by it, but there was nothing added to it. There was nothing squared or anything like that. So this is either r equals a sine theta or r equals a cosine of theta. So that could literally be 2 sine theta, negative 2 sine theta, 10 cosine theta, negative 10 cosine theta. But it's all being multiplied. Everything's to the first power. There's nothing times the theta. And so these have 2 different types. If it's sine, that means it's symmetric to your y-axis or your pi over 2. So if it's sine, it's in the top or it's in the bottom. it's a positive A, it's the top. Negative A, it's the bottom. And if it's cosine, now it's right or left. Positive A to the right, negative A to the left. And for all of these, A is your diameter length. So I start at 0, 0, and I end at A. Questions on circles. Circles are the easiest if you know what you're doing. You don't have to plug in any points. Okay, then we went to limicons. And these were the ones that were the most complicated. Limicons have 4 different types. This was inner loop, cardioid, or heart-shaped, dimpled, convex. All right. Remember that your shape can turn, so your inner loop is either right or left or top and bottom. I'm just going to draw them as one way, okay? But our inner loops could either be left and right or top and or bottom, depending on if it's sine or cosine, which we'll talk about, okay? And then it goes to cardioid, and then it goes to dimpled, and then it goes to convex. So we did them on the notes. They were on the x-axis, so I'm going to draw it like that just so that we can kind of like get an image. This-ish is your inner loop. Okay, then your cardioid has a point in it. It's like a heart. Dimpled looks like a kidney bean. These are awful, but you get the point. And convex has a flattened side. And again, these can get turned left to right, so the loop would be on the right, or the heart would be on the right, or the dimple would be on the right, or the convex, the flat side would be on the right, or they can go top and bottom. You know which one it is if it's sine or cosine. If it's sine and it's symmetric to the pi over 2 line, then it's going to happen at the top or bottom. If it's cosine, which would be all of these, because it's symmetric to your polar axis, it's going to happen on the left or the right. Convex looks like it's like if you took like a thing of clay and you chucked it at the wall, that flat side, it flattens it out. And the way we talked about it is I said, like, for me, I picture the flow of this. The very first one is my inner loop. And then if I physically took something and like pushed that loop out from the right hand side, if I was pushing against it, it would eventually turn into that heart shape. If I kept pushing, it would turn into the dimple. If I kept pushing, it would turn into the convex. So if your brain can see this from left to right, hopefully that helps. And then the way you know which one is which is your A and B values. So the equation for these are R equals A plus or minus B cosine theta, or A plus or minus B sine theta. That you will know it's a limicon if there is something added or subtracted from it. And then we're going to ignore the signs and we're going to grab A and B. And if A over B is less than 1, then it's an inner loop. If it is equal to 1, so they are the same, then it's a cardioid. If they are in between 1 and 2, it's dimpled. Sure. And if it's bigger than or equal to 2, it's convex. Mm-hmm. You're welcome. I promise you you're getting a limicon on your test. You might get a limicon and a circle. You might get a limicon and a rose. You might get a limicon and a lemniscate, but you are for sure getting a limicon. Huh? Yeah. You mean sine or cosine?
Yeah.
Yeah. So when I see it's a limison, the first thing I do is identify it's a limison. I find A over B. I figure out what that is, and then I figure out what type of limison. So when your test says classify your polar function, it's going to be a cardioid limison, a dimpled limison, a convex limison, or an inner loop limison. You'll have to say that. And then you'll give your symmetry. When you go to graph limisons, these are the ones that are going to require some work. So the first thing I do is classify it. The second thing I do is figure out the symmetry. The third thing I do is find the max. And the max is A plus B. Find your min. The order here doesn't really matter, but then you can find your min by doing A minus B. And then I find where the max happens. I set the equation equal to the max and solve for theta. And that will tell you where the biggest part of your graph is, or the rounded side. And then you'll know your min is on the opposite. And then you literally can plug in points from the top quadrants or the right quadrants and reflect it depending on the symmetry. Yeah.
So if B is already negative,
We ignore it. Ignore the sign when you do this. Yep. Yeah. The what? The rounded side. Oh, it says sine, but it should be side. So if you look at the graphs that are drawn, like if I had done this, let's just say I did it with this last one, right? If I did this with the convex one, I would have gotten like my max, maybe it's 4. I would have added the 2, 1, 2, 3, 4. I would plot my point there. I would figure out where it exists. This would be at 0, and I plot that point. And then let's say your min was 1. I know that happens opposite. So that's going to be where my right and my left is. This would have symmetry to the polar axis, so I would plug in points from the top of my graph, and then I would reflect it over to the bottom of your graph. Okay, next kind, rows. Okay, and your roses are R equals A cosine n theta, or R equals A sine n theta. I know it's a rose because it will have something being multiplied by theta. That's what makes it a rose. So when I look at an equation that says R equals 7 sine 2 theta, I know it's a rose. Same rules for symmetry apply. If it's cosine, it's symmetric to the pole axis. If it's sine, it's symmetric to the y-axis. She just asked to go. Yeah. So with a rose, if n is odd, then that equals the number of petals. If n is even, then 2 times n equals the number of petals. And A is the length of the petal. So for these, I figure out it's a rose. I figure out the number of petals. So 1, classify. 2, symmetry. 3, number of petals. And maybe I switch those because if it's odd, if it's even, there's more symmetry. 4, length of the petal. 5, set the equation equal to the length of the petal. And find where one of your petals exists. Yeah.
No, he asked me.
Oh.
And I was saying you. Yes, who decided this?
Oh.
Sorry.
It wasn't me, actually. I'll just teach you how to do it. Somebody came before me that was awful that determined that these were things you needed to learn. It's just my job to teach it to you. Eh? Yeah. Yeah, so if it's even, then it has polar, pole, and pi over 2. If the number of petals. Yep. If it's odd, it could have, if it's odd, it could have pi over 2 or polar.
It just depends on if it's cosine.
Correct. Yep. What? 5 says set the equation equal to the length of the petal. All right, then the last is called a limnoscate. Another made up word. And these are the easiest to spot because they have r squareds. They're the only ones with an r squared. So this will say r squared equals, and it's a squared sine of 2 theta. Or r squared equals a squared cosine 2 theta. A limnoscate is an infinity symbol. These, in order of easiness to graph, are like easiest is circle, next is limnoscate. I don't know. So these all have a symmetry to the pole. All symmetric to the pole. Okay? Not necessarily all 3 things. Okay, but definitely to the pole. It could have pole and pi over 2. It could have pole and polar. Or it could have all 3. Like if it's on the axis, it's going to have all 3. So for these, 1, we classify. 2, we find the length, or the r, the longest r, which we call this, like I call it a petal. It's not the official term because it's not a rose. But I find a, that's the length of the petal. Or loop, or whatever you want to call it, okay? Notice in the equation it's squared. So if my equation said r squared equals 25 sine 2 theta, then my a is 5. You have to square root it. Then I plug. Actually, we could do symmetry.
25 sine.
That's 25, yep. Find your symmetry for plug A in for R. And then that will tell you where the loop is, and then you find that the other loop goes in the opposite direction. You literally make an infinity symbol. So if I told you that when you solved it, if your loop was at the top, now I know the other one's at the bottom. If your loop was in the middle of the right-hand side, it's going to be the middle of the left-hand side. If it's in the left here, it's going to go right here. Like, so anywhere the first one is drawn, you literally just make an infinity symbol with the next one. It could be top, bottom. It could be right, left. It could be through the quadrants at pi's over 4s. Okay. Questions? So looking at number 1, it says sketch the graph of the polar equation r equals 6 sine 3 theta. What kind of polar function is this? This is 9.6. We did 9.5 already. It's a rose. This is a rose. How do you know it's a rose? You're multiplying something by theta. And it's not r squared. Obviously, if you're multiplying n, it's r squared. Now it's a limnoscate. But this is just a rose. How many petals does it have? 3. Yep. Okay, what's the length of each petal? 6. What kind of symmetry does it have? Pi over 2, because it's sine. Are we good so far? Didn't you answer those questions?
Not entirely.
Oh, okay. I was like, pretty sure you gave me the answer to a couple of those, and then you said you're not good. So then I'm going to find one of my petals by setting my equation equal to the length that it was given. So 6. So 6 equals 6 sine 3 theta. Once you know your length, you set it equal. Then I divide both sides by 6. And I get 1 equals sine 3 theta. And this is your solving of equations with multiple angles, which means there's something times theta. I have to figure out what angle it is first and then set it equal to that 3 theta. So where is sine 1? Pi over 2. So pi over 2 equals 3 theta. And then I'll divide both sides by 3 or multiply by 1/3. And I get my pedal is at pi over 6. So I get 6 pi over 6 would be that coordinate point. So I go to my graph.
Why did sine turn to pi over 2?
Because you're finding where sine, like you sine -1 both sides. You're finding where sine is 1. So now I go to pi over 6. I go to the 6th loop. 1, 2, 3, 4, 5, 6. And there's a pedal. Now where do we think the other one goes if it's got symmetry to the pi over 2? Opposite, over the y-axis, which would be where? 5 pi over 6. So I have another pedal here.
Oh, this is
It's a rose with 3 petals.
I thought it was the infinity sign.
Where could I put a third pedal so that it would still be symmetric to the pi over 2 line? At 3 pi over 2. Now how do I check that?
How'd you go on to look at that?
It's symmetric to your pi over 2 line. So you literally took this and reflected it over the pi over 2 line. If I wanted to check to see if this is a point, how do I do that? Just plug it in. I would plug in 3 pi over 2. I knew it had to be symmetric to the y-axis, and I can only have one. So like, how is something? If I put it here, there would be one there. So it doesn't work, right? I only need one more pedal. You'll never have all 3 in the same area if there's only 3. So I'm gonna check it. I'm gonna say 6 sine 3 times 3 pi over 2. 6 sine 9 pi over 2. 9 pi over 2 is not on my unit circle, right? But that is 4 1/2 pi. Where would that be? 4 pi, you remember our even odds? This would be 0. This would be pi. This would be 2 pi. This would be 3 pi. This would be 4 pi. 1/2 past it. I'm at pi over 2. You said pi. You said 2 pi. Oh, I thought you said 2 pi. Okay. Pi over 2 is correct. So the sign at pi over 2 is what? Sine at pi over 2 is 1. And now I get a coordinate point where I plugged in 3 pi over 2. And my r is 6. Confirming what I just found. Okay? So when in doubt, you plug in points. But you're going to use the different strategies depending on what kind it is to help you out. Correct. Yeah. If you don't know what you're doing, you have to plug in a bunch of points, you'll never finish the test. Yeah. Like a specific part. This is fine? Okay. All right. Go to 2. Classify it before I get there. Go to 2 and classify it. Go to question 2 and classify it. The situation between the 4 of you, and none of the 4 of you better ask me for help. 1, 2, 3, 4. Okay. Looking at number 2, and by looking at it, you should see that there's something that is added or subtracted there, which tells you it's a limison, right? Before I figure out what A and B are, what are you going to do? I'm going to distribute this 3 in. So my equation becomes 3 minus 3 cosine theta. So we said it's a limison. What is your A? 3. What is your B? 3. So A over B would be 3 over 3, which is 1, which makes it a cardioid or a heart shape, right? We talked about, like, if they're the same, maybe you're like, if they're equal, they're the same, they would be 1. Maybe they're like soulmates, so they have hearts, like inner loop. So so what kind of symmetry does this graph have? Good. Because it has cosine. That means anything that happens at the top is happening at the bottom, and that means that my heart shape, my little point, is either happening on the left or the right.
Yes.
Not at the top or bottom. That would be sine.
It happens on the x-axis.
Correct. Then I'm gonna find my max, and my max is what? 3 plus 3, which is 6. And I'm gonna find my min, and my min is 0, which should make sense because your heart goes to the origin, right? That little part goes to the origin, so that should always be 0.
For the min, do you ignore the sign too?
Yes.
For both max
Yes.
and
Ignore signs. Okay, so now I'm going to find where the max happens. I set my equation equal to 6. I'm going to subtract the 3. 3 equals negative 3 cosine theta. Divide by negative 3. Negative 1 equals cosine theta. So at what angle is your cosine negative 1? Pi. So that tells me my pi angle has the max point, which is 6. So I'm going to go to pi. 1, 2, 3, 4, 5, 6. And I plot my point. And that's going to be the rounded side. And the min is going on the right, which means my heart is there.
Yes.
So it's going to look something like this. I'm going to get more accurate than that, but I at least know that shape. You with me so far?
Yes.
Wait, yes.
So max is at pi.
So that's how you find what rounded side is
Correct.
doing the max.
And then the min is always the opposite. So if my max is at pi, my min is at 0.
So min is where like
The heart happened, yeah? The pointy part of the heart. Yep.
So it doesn't have anything to do with it being a negative cosine?
That tells you that the heart's on the right-hand side. But like we said, we're going to find the max anyway, so you might as well just set it equal. Okay. Now, when I go to graph this rounded side, you really probably only need 1 point. So I'm going to pick 3 pi over 4, and I'm going to plot it. So I plug in 3 minus 3 cosine 3 pi over 4. 3 minus 3. The cosine at 3 pi over 4 is negative root 2 over 2. And I get 3 plus 3 root 2 over 2. Yep.
Are we getting a calculator?
No, we're going to approximate. So remember we said 2, root 2 would be 1.4. So this is 3 plus 3 times 1.4 is 4.2 over 2, which is 2.1, and that's 5.1.
Yeah, that's good.
so to plug in points you just plug in a pi.
So you're going to plug in any of your special angles, but because I only really need 1 over here, like on the rounded side, you really only need 1. So I just picked the one in the middle. But I could have done over 6. I could have done over 3. So I'm going to make that 5.1. So 1, 2, 3, 4, 5.1. And whatever happens above is going to get reflected lower because this is symmetric to the polar axis. So at 5 pi over 4, I go to 5.1. Whatever happens above your axis happens below your axis if it's cosine.
What is it? Where's this 3?
And if it
Square root of 2, what is it pointing to?
Root 2 we approximate to be 1.4.
And then let's say it was like on the what's the y-axis called?
The pi over 2.
But like it's polar and
It's pi over
the
two,
y
yeah.
over 2. The pi over 2. And
So
then
if
let's say it was
this-
that, then it reflect this.
Correct. So if it's sine, I do the right side. If it's cosine, I do the top, reflect it over the bottom. If it's sine, I do the right side, reflect it over the left. Yep. Okay, so now I need to find, because this part of my graph has the heart, I want it to be more accurate. You're going to pick 3 points from that section. So I would pick pi over 2, pi over 3, and pi over 6. So I'm going to plug those 3 in. Pi over 2, pi over 3, and pi over 6. Honestly, with a heart, you don't need it to be that specific, but with a loop, you're definitely going to need the extra points. So we're going to practice it that way. So I'm going to plug in pi over 2. 3 minus 3 cosine pi over 2. What's cosine of pi over 2? 0. So this is 3 minus 3 times 0, and that is 3. So at pi over 2, my coordinate point's at 0, my radius is at 3, which means at 3 pi over 2, it is also 3. Then I go 3 pi over 2. 3 minus 3 cosine, or sorry, pi over 3. Oh, I said that. And the cosine at pi over 3 is? Good job, 1/2. 3 minus 3 halves, or 3 minus 1.5 is 1.5. So 1.5 And it's going to get reflected down to 5 pi over 3, 1.5. So again, with a heart, we'll stop here because we don't need another point. With a heart, that's plenty. One from each quadrant reflected down. With an inner loop, you're probably going to need at least one more. So I would have also done pi over 6 and to get that loop on the inside. So this shape looks like that.